after few line of code, then you will automatically understand, okay, this thing. Let me create the model. Okay, let me write the function. As we know, our aim is to, you know, predict the 80 from the which one, waste, right, from the waste column, isn't it? Right, so we just created the formula for this, and we are providing the data. And which data we are providing? The our WCAD data we have. And after that, after building the model, what we can do, we can simply fit this particular ordinal least square model, okay, to fit our regression equation. Okay, so that's it, dot fit, which means that create the model in short. Okay, we are commanding to our system like build the model like this, okay, which can, you know, show you the formula like this is the y value, this is the x value, this is my data, okay, and build my model. That's it. Okay, we are just commanding to my computer or to my laptop saying that build my regression model by using this particular line. Now see, it is taking some time now, right? It is taking some time. You will see that now we got the output, right? This is x coordinate, this is y coordinate, right? So if we're talking about the y and x, so it will be very relatable for us. Okay, this is y, which means that this is my target column, and x is equal to my input feature, okay, that I'm gonna use to build the model and which can predict the 80, right? Let us go ahead, guys, and see the parameters that we find out. Okay, this is my model dot params. Okay, I'm just finding out the parameters for this. Now here you can see. Now basically I use the OLS, ordinal least square regression, to find out the intercept and waste column coefficient. Now this is nothing but, as I explained over here, okay, over here, let me show you, y equal to beta naught plus beta 1. After estimating, you will see that the y hat, which is nothing but the y estimated, equal to beta naught plus beta 1 x. Okay, now here we just find out, or we just estimated the values of intercept, which is beta naught here, and beta 1, this is the value of beta 1. Okay, with the help of OLS. OLS is one of the method, ordinal least square method, right? We just use this particular method to estimate our coefficients of regression equation. Okay, now we are ready to use our regression equation. Okay, my regression equation is ready, okay, in the form of my model. Okay, instead of using y equal to beta naught plus beta 1 x, I can simply use the model, right? Model from now. Okay, now what I can do is I can use this model for the prediction. Okay, so I'll use this model for the prediction now. So for this, let me store the predicted value as the predict. Okay, pred. I'm gonna use the model to make the prediction, okay, of my past data, okay, which is there. Beta 1 again for this particular model. This is beta naught, guys, and this is beta 1. Okay, as I mentioned earlier as well. Okay, this is beta naught. Beta 1 is nothing but the, you know, as I mentioned, beta naught is intercept, right, and beta 1 is slope, right? So beta naught is intercept, so intercept value is here. You can see intercept word is here, and the value for intercept is here. Okay, so beta naught is this and beta 1 is this. Okay, okay, guys, so let us go ahead and make the prediction by using a predict function. Okay, and I'm gonna use now ilock method. Okay, why I'm using multiple methods over here? Just to show you how you can use these methods. Okay, and wherever you can, you, okay, like where you can use this method, right? So let me go and make the prediction. Okay, now we got the prediction. Okay, so now what I can do is I can simply build my model. Okay, which means simply, you know, I can show you how you can, okay, how we got the, you know, the plot. like I show you this particular thing, okay, this particular line and dots and all, that's what I can show you over here right now. Okay, so for that, let me create a scatter plot. Okay, scatter plot. I think, I guess we just created over here. Okay, so let me just copy the scatter plot from here. Okay, it will be very easy. Okay, this is my scatter plot I just created. Okay, now the second thing is that, okay, let me go and use the plt.plot. Why I'm showing you is this, okay, because if you see that the first thing, okay, I show you this thing, okay, the scatter plot, and secondly I'm showing you the plot for the line, for the regression line we are creating, right? So let's go and create the regression line now. Okay, so again I'm gonna use this particular thing, paste, okay, as x, and as y I'm gonna use the predicted value. Okay, as y I'm gonna use a predicted value, right? And now here you can see, now let me use the color, which is the, let's say, different color I'm gonna use, because you will see that for the scatter, the default color for the scatter plot is going to be blue. Okay, so I'm gonna use this color as a, let's say, red. Okay, so that will help, okay, us to to see the line, regression line, right? Okay, now let me label it. Okay, label it like in the scatter plot. Okay, there is no label, okay, to understand what is this. Okay, like what is this axis mean and what is this. Okay, so that's why I'm gonna add the labels over here. So that's why I'm gonna use a plt again, x label, right? And in the x label we have the waste. Okay, and in the, again in the y label you will see that, y label you will see that the adipose tissue, our 80, right? Okay, now let me go and run this. Okay, now see here I got the error, plot is not defined. Okay, so what I can do is, okay, name error is there. Okay, see plot. Okay, and now, okay, here you can see that instead of plt I wrote the plot. Okay, my typo, my bad. Okay, so let me go and run this again. Again I got the error, that's cool. Okay, again here you can see, okay, I got the again error. What is it, what it is saying, plot got an unexpected keyword argument. Now let me go ahead and remove those unexpected arguments, because in the scatter plot we can add the x and y, but in the plot we can't add the x and y, we can simply add the names. Okay, so I guess, okay, this time it might work. Yeah, so now see, is it okay, we are able to the see the regression line, we are able to see the regression line. See, so that's how you can create the model. Okay, now see the summary of the model. Now see the summary of the model. Now you can see that the summary, let me go and run, and now you can see the beautiful summary of this particular regression model. Okay, why I am saying beautiful summary, because you will see that the lot of evaluation matrices it can provide to me, okay, by using just the stats model library. So stats model library is very much important, guys, if you wanted to see the summary like this. Okay, and this is the only model which can give you the summary like this. Okay, this is the only summary, okay, just given by this particular library only. Yeah, and in that you will find that the what is dependent variable over here, which is 80, which means this is my target column. Okay, I have to build a model for this particular to predict my 80 adipose tissue area, right? Okay, which model I have used, OLS, ordinal least square model. Then which method I have used, least square method I have used, the date I have executed this particular model on this particular Jupyter notebook, the time, number of observation over here, 109 observation, yes, in my data. Yes, degrees of residual, this is another part, because again, okay, if I go with this, the description of this, so again it will take me 15 to 20 minutes. So let's forget about this term. Okay, the df of the model, these are nothing but just the degrees of freedom. You can note it down, and you can, after the session, you can search on the internet what is degrees of freedom of the residual and what is degrees of freedom of the model, right? Then covariance time is non-robust. Okay, now after, let us go ahead and see the few evaluation matrices which are there, okay, mentioned in the the agenda in the today's session. You can see that the r square. Now what is r square? R square is nothing but the showing you the how accurate your model is. Okay, your capability of your model, right? Adjusted r square, here r square is nothing but 0.67. 0.67 is nothing but the 67% of variation. Okay, the variation of this particular data, your AT data, explained by your waist column. Your waist column, which means you just collected the waist circumference data, isn't it? Okay, right? So after collecting this data, yes, how much this is helpful? Okay, this data give me the 67% of information for this AT column. Now what about adjusted r square? So we'll be talking about the adjusted r square, okay, when we are creating the multiple models. Okay, and we'll see which model giving me the highest r square value. Okay, if out of, let's say, 10 model I have built, and out of that model, okay, one model giving me the highest accuracy, so that is nothing but the highest adjusted r square value. So I can say that particular model is the best model to make the prediction, to make the future prediction. Accuracy is not the r square is not the accuracy of the model over here, because accuracy is somewhat different. Okay, r square is somewhat different. Okay, we'll be talking about the accuracy in classification. Okay, but in regression we'll be talking about r square most of the time. Okay, yes, how to identify? Yes, that's what I am gonna tell you. So here you can see r square value. If your r square value is 67%, which means that 67% of the time, okay, 67% information of the your AT column, your target column, is you can find out from the waist column only, right? So we can say, let's say if your r square is 90%, okay, let's say your r square is 90%. Okay, so which means that, okay, 90% of your AT columns information, okay, which is given by the waist column. Okay, that is the thing. So guys, after this, here you can see that adjusted r square, as I told you, if you are creating multiple models, so at that time you will need to see the adjusted r square value. Okay, whichever model giving you the highest adjusted r square value, that model is you can use, that model you can pick to make the future prediction. What about f statistics? Okay, so f statistic is just the value. Okay, you just wanted to see the p value of the f statistics, which is this. Okay, and if this value is less than 0.05, okay, so there is a hypothesis test of f statistics. So okay, so in the f statistics, okay, which is saying that the null hypothesis for this is to model is significant for making upcoming predictions, and model alternative hypothesis is model is not significant for making the future predictions. Okay, p value is nothing but the value of the your, what I can say, your, the point, okay, from where you can decide, okay, your model is significant or not. Okay, so the not the default value, you can use any p value, but most of the time we are using the p value as a 0.05. So here you can see, Okay, you can see here, okay, the value is nothing but 0.00000, very less value, because e raised to minus 27 is there. Okay, which means that around 26 zeros are there before the one value. 0.26 times 0 value is there, and then 162, so which is absolutely less than 0.05. So I can say, okay, which means that, okay, I'm just accepting the null hypothesis, and null hypothesis saying that my model is significant. So guys, that is the statistical part. Okay, like that is a statistical part. Why do we wanna match the probability and hypothesis here? Because to show you that our model is significant or not for making the future prediction. Okay, how you can check your model is strong or not for making a future prediction? So by using this, you can check your model ability, right? The ability of your model, right? So that's why hypothesis testing, probability is again the very much important. Okay, if you know that, so it will be very easy to go ahead in the machine learning as well. In fact, there is one algorithm is there, okay, in the machine learning, which is nothing but the naive Bayes algorithm. You can search for this naive Bayes algorithm. You will find that that algorithm is totally based on the one theorem, which is nothing but the Bayes, and that theorem is totally based on the probability. Okay, which means probability is very much important in machine learning for creating the models. P value, okay, p value should be less than 0.05. Okay, p value should be less than 0.05, then only you can say your model is significant. Okay, now log likelihood is there. Okay, now log likelihood, AIC, BIC, these are the criteria. Akaikis information criteria is there. This is the Bayesian information criteria is there. If you wanted to see this criteria, and from this criteria, if you wanted to decide whether your model is strong or not, so what you can do is try to check these values, okay, are close to zero or not. Yes, my these values, if you are using building the 10 models, and you are checking the AIC, BIC or log likelihood value, so try to see these values, okay, are close to zero or not. If the any model giving you the AIC, BIC log likelihood value which is very much close to zero, so that model is, I will definitely okay, tell you that that model is 100% correct and strong model, right? So okay, these are the few statistical terms. Okay, if you wanted to explore deeper into it, so you are just free, feel free to explore more about this in on internet. Okay, or you can definitely come to me on on LinkedIn. I'll share the some resources with you, so you can explore this thing. Okay, now this is the second table. Okay, now this is the first table. From here you can decide your overall model is significant or not. Now from this second table you can decide your each and every column is significant or not, like my waste column. Okay, if you have the multiple columns, so you can say your multiple column is significant or not, right? And these are the few statistical tests. Okay, with this test you can simply check, okay, again your model's credibility. Okay, now I'm not going into it. Okay, but okay, again, because it will take so much time. Okay, so okay, these first two table are very much important. T means the T distributions test. Okay, T means the T test, and this is the probability of T test, and this is showing that the probability value is 0. Okay, which means that p value is less than 0.05. So I can say this intercept is just making a significant effect, okay, on making the prediction, as well as the waste column also making a significant effect on making a prediction of upcoming data. So I can say this model is good, but again R square value is not that much good. Okay, so you can go and make the further changes in your model, and you can build the model again, because see, this is just the two columns over here. Okay, there are just the two columns over here. That's why you can, okay, we can get the R square like this. Okay, you can improve the R square by using the manipulating your independent data. Okay, again, that is a different case. If you wanted to explore more about this, like like we have the one course for that. Okay, you can check that as well. Okay, because that is again the which is some kind of some detailed situation, I can say. Okay, so let's go ahead. And okay, this is about the simple linear regression. Okay, now let us understand. Okay, because okay, this is the base. Okay, now after this thing, if you understand this thing, so it will be very easy to understand the multiple linear regression. Okay, so let's go ahead and understand the multiple linear regression now. Data set, which is nothing but the cars data set. Okay, and as you know, we just imported the all the library which are necessary to read the data, to plot the data, and all, which is nothing but we already imported this. So again, in the same Jupyter notebook, you don't have to you know again import this library. So you can simply go ahead and use the cars data. And as we know, and let me run this. Okay, now here you can see that my cars data. Okay, cars data dot head, and here you can see this is my car data. In the car data, you will find that the horsepower of the vehicle, okay, of the car, mpg, miles per gallon, right? This is my target column. Okay, like in the previous case, my target column was 80 adipose tissue area. Now here my target column is nothing but the mpg, okay, mile per gallon. Now here you can see that first horsepower of the vehicle, volume, okay, the space inside the vehicle, okay, then speed of the vehicle, highest speed, and the weight of the vehicle, right? Okay, now after this, let's say, and go the do the same thing as we did before. Okay, you can go with the multiple different things, but in the simple words, as we know, as we did this thing, has as we created the model like this. Okay, we are using the same thing to create the model over here as well. So again, okay, this model is again the pre-process already clean model, because I in the model, okay, if we sit for the data cleaning, okay, it will take more than 1 hour and 30 minutes. Okay, if you are professional in it. Okay, otherwise it will take 80% of your project time. Let's say there is a project time 30 days, so it will take around 24 days, I guess. Okay, to clean your data, just to clean your data, nothing else. Okay, what about else? Okay, let's go ahead and use all the data over here, remaining columns. As we know, hp is there, plus volume is there, plus speed is there, plus weight is there, right? And my data is going to be the WCAT. Okay, not the WCAT, is going to be the cars, right? And after this, let's go and run this. Here you can see my model is complete, and let's see the my model. Okay, model dot params. Okay, these are the parameters now. Okay, now my model is not the just two coefficient. Now model has the 5 coefficients. First intercept, then beta 1, beta 2, beta 3, and beta 4. So you can see over here. Okay, as I told you, the this thing. Okay, y equal to beta naught plus beta 1 x1 plus beta 2 x2 up to so on beta n xn. That's what, okay, we can see over here: beta naught, beta 1, beta 2, beta 3, beta 4, and these are nothing but the x1, x2, x3, x4, right? So these are the different things you can see over here. Now guys, okay, this is the thing. Now let me go with the summary. Okay, the model dot summary. Okay, and summary is the method, so that's why I have to go with the the brackets. Okay, round brackets. Now here you can see. Now again I got the same output. Okay, the same summary. Okay, I got the dependent variable, which is nothing but the miles per gallon. My model is ordinal least square. My method is least square method. When we executed my model, okay, at this date, at this time, how many observations are there? Okay, 81 observation. Degrees of freedom for the residual, which is nothing but degrees of freedom for the error. Okay, degrees of freedom for the model. You can see now the 4 degrees of freedom here, because you will see that the you just created the 5 parameters, okay, and total parameters minus one is going to be your degrees of freedom for the model. Let us talk about the different evaluation matrices you're gonna use. Okay, so simply here you can see that just by using the 82 observations, you can see total data points are nothing but the 81 number of data, number of observations or number of rows are there, total 81 are there, right? So just by using 81 rows and how many columns, here you can see only 5 columns, and out of 5 column, one column is the target column. So except this column, only 4 column is there. So with the help of this 4 column, okay, we can build the model which can predict the MPG, mile per gallon. Degrees of freedom for the residual is, again, I told you that it's a statistical term. Okay, to explain this particular term, again, we'll need to again a lot of time to understand this term, because it's a very deep meaning term. Okay, just from from the you can just try to understand this, not the deeper, just overall, I can say it's a degrees of freedom for the error. Okay, degrees of freedom for the error. And the degrees of freedom for the error is nothing but the total observation minus your number of parameters you wanna just create, you wanna estimate in your model. So here you can see I just estimated total 5 parameters, right? Beta naught, beta 1, beta 2, beta 3, beta 4, to total 5 parameters are there. And total how many observations are there? 81 observations. So 81 minus 5 parameter, which is nothing but the 76. This is the degrees of freedom for the residual. Okay, degree of freedom for the, okay, so R square value here is 77.1%. Now here the interpretation of R square value is that, okay, there is 77% of variation or percent of information of MPG, miles per gallon column, which is explained by these remaining columns, which are nothing but the horsepower, volume, speed and weight. Got it? Okay, which means that, okay, this model is again, again you can say that the somewhat, again the powerful model. Okay, again here also you can make the changes in your model, so it can increase the R square value, so automatically the remaining values will also increase, except these three it will reduce. It will definitely reduce if you go ahead and make changes which is positive changes, not the negative changes. Okay, so it's like a trial and error method. Okay, to see, okay, whether you're, if you are adding someone, okay, some new feature, so which means that it will definitely just show you the throw you the R square is, sometimes maybe higher R square, or sometimes maybe lesser R square, depending upon the power of that particular new variable. Okay, so at that time you will see that this, okay, this values will increase, and these values you will see that will decrease, will tends to 0. If your model is good, this value will be very much close to 0. Let's say 20, 40, 80, like that. Okay, now it's a 3 digits value. Okay, then, okay, if your model is so strong, then you will see that the this value will be in 2 digits or either 1 digits. Okay, if the R square value is tends to 1, then you can see that your model is good, your model is strong. If you say your R square value is tends to 0, or very much close to or less than 0.6, okay, then you can say that your model is poor model. Okay, you will have to do something to make the strong model. How you can, okay, how to calculate the R square? Okay, so for calculating the R square, you need to know the sum of square due to regression, sum of square due to error, and sum of square due to total. Okay, yes, Yeah, the formula for creating this 1 minus sum of square due to first regression divided by sum of square due to I guess error, right? So by using this particular formula, you can simply find out this. And now what is sum of square due to regression? What is sum of square due to error? Okay, these are the, again, the statistical term. Okay, that's what I just wanted to show you. Okay, okay, if you go into the deeper of this linear regression or the multiple linear regression, again, it will take so much time to understand this thing. You will find that these all are term. Behind this term there is one formula, and in that formula there are few terms. Okay, and again behind those terms there are few things, right? Okay, like behind RSS, residual sum of square, there is much more thing. Okay, the formula of RSS is nothing but the summation in in the bracket. You will find that the your values minus that estimated values. Okay, the estimated, which means the error. Okay, your original value and your estimated value, and bracket square like that. Okay, and divided by divided by divided by n minus 1. Okay, so this is the thing. This is just the formula for the residual sum of square, right? So like that, if now, okay, you will have to understand what is x and what is x hat. Okay, right, these are the estimated values, I can say. Okay, x hat, y hat in terms of. So here you can see the HP column. Okay, okay, this is the intercept. Intercept is the coefficient value. This is not the variable. Okay, if you talk about the HP column, so here you can see, you can go over here. Okay, this is again each and every term. Okay, will have the separate meaning, guys. Okay, will have the separate meaning. This is the coefficient, which is nothing but the beta 1 value. Okay, this is the standard error for this particular column. Okay, HP column, you will see that the standard error for this. Okay, this is the t-test value, and this is the p value for the t-test. So most of the time, okay, if you know all the thing, you can simply go ahead and you can see the p value, like I am seeing. Okay, if you know all the things, you can go ahead and see the p value, right? Because I know all the things. Okay, like the what is t value, how you can calculate the t value, what is the reason behind the t value, how you implemented t value test over here. And lastly, here you can see this is nothing but the confidence interval. Okay, like as I told you in the yesterday session. Okay, the about the confidence interval. Now let's come to the topic and see. Okay, understand. Okay, like one by one. Okay, like this HP is significant or not, volume is significant or not, like this. So here you can see HP, the p value for HP, you can see 0. And as we know, if we compare with our p value, which is the default p value, I can say, or most of the time we are using p value, which is nothing but 0.05, and the p value here is 0.000. Okay, so as we know, this p value is less than 0.05, right? So we can simply say that HP is the significant column for making a prediction, okay, of about the MPG. Okay, which means that this column is the something significant column which can make the prediction or about the MPG column, right? This is the first column we can see. Okay, what about second? This is the volume column. Okay, in the volume column you can see the p value is 0.556. So as we know, if we check with p value, which is 0.05, so here p value is higher than this, right? So here our p value, the default p value is 0.05, but our p value, which is this 0.556, which is greater than 0.05, which means that this particular column is insignificant column. This volume column is not contributing, okay, in our model to make the prediction about MPG column. Now this is the insignificant column. In the same way, okay, if we check for the SP column, so you can see 0.015. Okay, again we can say that if we compare with our p value 0.05, so this value 0.015 is less than 0.05. Yes, so this is again the significant column, I can say. Understood? What about weight column? So weight column, here the p value is 0.814. So here you can see Okay, the p value for the weight column is 0.814, which is greater than 0.05, which is the default value of p value. Okay, or most of the time we are using this. Okay, so if the p value is greater than 0.05, so in our case this is greater than 0.814, which is greater than 0.05, right? So again, this column is also insignificant column. This column is not contributing to make the prediction about the mpg, right? So out of 4 column, okay, 2 columns are the insignificant columns, which means these 2 column, volume and weight, which are not contributing in our model. And these 2 columns, okay, the hp and speed column, are contributing positively, right? Contributing very strongly to make the prediction about the mpg column, and that prediction is correct. And these 2 columns are contributing negatively, in negative direction. Understood? So that is the thing. So that's how you can find out which column is, contributing in your model and which column is not contributing. So that is about the multiple linear regression, guys. Okay, as we saw the simple linear regression and multiple linear regression, we also saw the evaluation matrices. What are the different evaluation matrices are there? What is the R square? Okay, what is the different evaluation matrices? Adjusted R square, F statistics, and remaining all this. Okay, there are, okay, there are lot, right? There are lot. Okay, just the thing is that you will have to explore it, right? You will have to explore it. Okay, and for that, like I created a one course, which is, I guess, around more than 100 and 120 hours of course, I guess. And in that course, okay, I'll be trying to explore in very much more deeper. So each and every concept will be clear like that. That's it about the session, guys. Thank you, guys. Thank you very much for being with me, and thank you very much. Bye bye.